let's take a quick look at a few classic calculus problems that you'll see throughout your time in this calc class. One of them being the tangent line problem, and another one later on being an area problem. Now, a tangent line here you can see at the left is where it touches at a particular point, but only touches at one point. It's a little bit hard right now with our pre-calculus knowledge to find the equation of that tangent line. Because as we know, in order to find the equation of a line, we need a point and we need a slope. But we only know how to find the slope if we're given 2 points, right? Our slope formula, y2 minus y1 over x2 minus x1. So it's a little bit hard for us right now to find the slope of that line if we're only given 1 point. So what we're going to use when we start to learn our calculus is we're going to use the limit process, where we're going to actually start by using a secant line that maybe touches at 2 points. You can look over to the right here to see that maybe our secant line touches at point P and point Q. And we're going to take that secant line and we're going to use the limit idea that we're going to learn to move those 2 points closer and closer and closer together so that eventually it only touches at 1 point, at point P. And we're going to use that idea to find the slope of our tangent line. It kind of goes along with the idea of velocity. So velocity, even acceleration, is something that we're going to talk about also in this class. Now before, we've talked about constant velocity in our pre-calculus classes, but now we're going to talk about varying velocities, right? If something doesn't move at the same exact rate all the time, how do we figure out how fast it's moving at a particular instant? An average velocity versus instantaneous velocity is what we're going to use in our calc class now. So a quick example, if you were on Mars and you threw a rock upward with a velocity of 10 meters per second, we can find the height t seconds later given this equation y equals 10t minus 1.86 t squared. Now we can use our pre-calculus knowledge to find the average velocity, right? The velocity, how fast it's moving over a period of time. Really, that's just a fancy way of saying find the slope. Find the slope between 2 points. We want to figure out the position over time, right? So if I asked you to find the average velocity from 1 to 2 seconds, we can use our slope formula, our y2 minus y1 over x2 minus x1, and we can calculate that it's on average moving at a rate of 4.42 meters per second from 1 to 2 seconds over that time interval. Now I can ask you to move that time closer and closer. I can ask you to find the average velocity from 1 to 1.5 seconds. Using the same idea, we can calculate that on average, my speed, my velocity, is 5.3 meters per second over that time interval. I can get even closer and closer and closer, but still technically only finding an average velocity if I'm talking about 2 instances in time, right? Or a range in our time. But what if I asked you to find the instantaneous velocity? How fast is this rock moving at exactly 1 second? Well, this is where we're going to use our idea of calculus and the idea of limits to move those times so close together so that we're eventually just talking about 1 second. Now we can estimate by using our numbers up above, and we can estimate that it looks like it's getting closer and closer and closer to about 3 meters per second. But we can actually use calculus to find the exact instantaneous velocity at exactly 1 second, which actually happens to be 6.28 meters per second. So we'll get into that soon. One of the other problems you might see later on in calculus is the area problem. If I give you a curve and I ask you to find the area underneath that curve from a certain interval, right, from A to B, how are we going to find the area underneath this curve if it's so curvy, right? Well, without calculus, we can estimate the area underneath the curve by using rectangles. We know how to find the area of a rectangle, base times height, so we can estimate by putting a bunch of rectangles underneath our curve. But you can see in our picture that some of the rectangles are above the curve, some of them are below the curve, so it's still just an estimate. It's not an exact area underneath the curve. So how can we get the exact area? Well, we can use our limit ideas by taking our rectangles and adding more and more and more rectangles so that eventually we have an infinite number of rectangles that's going to fill up exactly the area underneath this curve so that we can find the exact area and not just estimate it.